Assalamu alaikum student. This is the video lecture number 3 of week number 14, and this lecture is also the continuation of the conservation of linear momentum. Which is a topic in chapter number 5, and we are discussing the fluid flow through the pipe bend. Okay, so the topic, obviously, the fluid flow through the pipe bend and the practice problems, that means some numericals we are doing. So before we have discussed the pipe flow through the bend with uniform cross-sectional area. Okay, but now we are going to discuss uh, the fluid flow through the pipe bend with variable diameter. Okay, that means the dia is the elbow is reduced diameter. So here you can see one example. Okay, so which is written here. The consider uh, excuse me. Consider a flow through a copper pipe bend. So first the material is copper pipe, okay, bend as shown in figure. The flow enters the bend with a speed v1, okay. The entering velocity is v1 and leave it as a speed of v2, and the leaving velocity is v2. The corresponding area of cross section being A1 and A2. Okay, so the cross sectional area at point 1 is A1. So this is area, this is the section 1, we can write, and this is the section 2 at point 2. So the area at this point is A1 is given, okay, and area at this point is A2 is given, the cross-section area. Okay, all right. The velocities have components u and v in x and y direction. Okay, all right. See, the velocity is given and it has a component u and v. That means it's a two-dimensional flow. Okay, and it has x, u and v component. That means we have u, x and y component. Okay, so as the flow negotiates the copper pipe bend, okay, whenever the flow enters and when it approaches to the bend, when it approaches to the bend, it negotiates, okay, exerts a force upon it. So there is it exerts a force upon it. Okay, so it exerts a force upon it. So this is x direction and this is y direction, and this is the force exerts on the bend. Okay, so this we can call it F. Okay, and then Fx and Fy. Okay, so this force is readily calculated by the momentum theorem. So let's see, if the pipe size is reduced, then how we can calculate the force exerted by the fluid on the pipe bend when the given material of the pipe is copper. Okay, so here the continuity equation, by using the continuity equation we can calculate the mass flow rate. Okay, the flow is the density of the fluid is rho, velocity is given at point 1, velocity is cross sectional area is given at point 1. So this is the mass flow rate at point 1 and this is the mass flow rate at point 2. Okay, so this is given. So we can calculate the mass flow rate by using this continuity equation. Okay, so now carrying out a force balance in x direction. So according to the law of conservation of linear momentum, it says the net force acting in a particular direction is equal to rate of change of momentum in that particular direction. Okay, So now we are going to analyze the forces and momentum, rate of change of momentum in x direction. So first we are going to see what are the forces acting on the uh, surface, okay, uh, on the surface in x direction. So this is the component which is fx, okay. So this is fx and this is the component which is fy, okay. So this is fy. So the net force in x direction, what are the forces? This is the pressure force P1A1, okay. So this is the pressure force at point 1 in x direction, okay, and the P2A2 cos theta, is that a force acting in x direction? Is it a force acting in x direction? Is it right? Uh, Please, one thing you must note that it is not given here that the the velocity v2, when the velocity leave the pipe bend, uh, it leaves in y direction or it leaves with a particular angle. So it is not given, it is general, it is leaving with any particular angle, okay, through the discharge, okay, but the area of cross sections are not same, velocity are not same, okay, and the angle is not given. So the velocity v2 is leaving through the elbow with any angle theta, okay, that we don't know, okay. So that's why the pressure at point 2 will be equal to P2A2 cos theta. So if it is 90 degrees, so this factor will be 0, okay. If this is 0 degree, if it is become a straight pipe, so it will become just like a not pipe reducer, is only reducer, so it will become 1, there will be a component, okay. So uh, okay, if it is 45 degrees, so if it is leaving, if it is 45-degree elbow, the cos theta will be for cos 45. So since angle is not given, so we cannot eliminate. Since in the picture it is very obvious, it seems vertically upward, okay. But here we are considering that it is not leaving vertically upward, it is leaving with a particular angle. If it is 90 degree, theta will be 90 degree and straight away this factor will be cancelled. But we are taking a generalized term, okay. So here P2A2 is equals to P2 cos theta plus the force exerted by the fluid on the surface, that is Fy, sorry, Fx. This is the factor, it is also in the positive direction. So since it is this, basically the direction is wrong, the pressure is always acting perpendicular to the surface. Always the pressure acts like this, okay, perpendicular to the cross-sectional area. So that's why it is the direction of this force is negative, okay. So because it is making some angle, it is making some angle theta, okay. So it is, if this is theta, so the component of this Pa2A is, this factor is negative because this is in this direction. So minus P2A2 cos theta plus Fx, this is in positive direction, so positive. And rate of change of momentum in this direction. So what is the velocity at V1 is equals to, what is the velocity at V2 is V2, okay. And we are considering any angle, since if it has some angle, so we are considering it also has some angle, it is discharging with a particular angle, okay. So we are considering this is theta, this is theta, and this is its x component, sorry. So this is going to be all right. So this is the x direction and this is the y direction, okay, at any angle, okay. So in that case, this will be the resultant, okay, and this will be the x direction and this will be the y direction, okay. So this will be the component of force. So that's why, so rho V2 A2 and V cos theta, the component of this, okay. And same, this is obvious, it's in horizontal direction, it is connected with the pipe in the horizontal direction, okay. So it is rho V1 A1 into V1, okay. So when we simplify that, the mass fluid will common, okay, this will become V2 cos theta minus V1, okay. All right, so what we can do now, analyze the force in the y direction, okay. So this is in the y direction, there is no x component of force in the, there is no fx1, okay. And this is, uh, there is a force in the y direction, okay. There is no pressure force in the y direction at point 1. So there is a pressure force at point 2, there is a component sine theta, and there is a force Fy, okay, the reactive, the force exerted by the fluid on the surface, and there is a change in momentum, okay. So since in the y direction there is no velocity, so that's why the momentum is 0, okay. So after simplifying this, this will become P2A2 sine theta plus Fy is equals to m dot V2 sine theta. Okay. So this then simplify the x component and y component. So the x component will become this and the y component will become this. Okay. So if you know theta and if you know V1 and V2 and the area and the pressure at inlet and exit, you can easily calculate the x component. And if the flow, if the pipe bend is making any angle, you can just put and you can calculate the values, okay. So second, and here you can calculate the y component, okay, in this case. When the fluid entering to the pipe bend horizontally and leaving with a particular angle, okay. So in this way, these two equations are useful and we can directly use it. So let's see one example. Here, a flow of 300 liter per second of water passes through the vertical 300 to 200 diameter reducing pipe. Okay, so this is the point 1. Okay, and at the point 1, we have a cross section area. Sorry, we have a pipe diameter which is 300. Okay, the 300 is given at the inlet at point 1, and here the area reduced or the diameter reduced, so which is become 200. Okay, so this is basically a reduced pipe, you can see here. Okay, all right, reducing pipe bend is sketched below. The pressure at the entrance is 70 kilopascal. The pressure is given at the entrance. Okay, the bend has a vertical height, it's the bend is too big, okay, so it has a height 1.5 meter, okay. So that means the 300 and 200 pipe is basically is not too big, but the radius is too big, okay, to reduce the friction loss, okay. All right, so the bend has a vertical height of 1.5 meters, so it has taken 1.5 meter from the center line of the inlet, okay, from the center line of the inlet, okay, of the inlet to the center line of the outlet. So this is the center line of the outlet, okay. So the center line of outlet and the center line of inlet. All right. uh, and the volume of the bend is 0.08 meter cube. Okay, the volume of the bend is given. Okay, this volume is given. Okay, so what force, magnitude and direction both we have to calculate, is required to anchor the band in place. Ignore friction. Okay, so we have to saying no friction loss. That means P1 is equals to P2. P1 is equals to P2, no friction loss, and it's also given the velocity. It is discharging with the velocity theta, which is 120 degree. Okay, students, so P1 is equals to P2. Because of that, as I said, ignore friction. There is an advantage of it. So, based on that, we took P1 is equals to P2. Now, to solve this problem, what are the informations to be known? So, first of all, we should know the pressure at this cross section 1, the area at this cross section 1, and the velocity at the cross section 1. Similarly, the area at cross section 2, the pressure at cross section 2, and the velocity at cross section 2. So at cross section 1, we know the pressure, and the cross section area is not known, but the diameter of the cross section 1 and cross section 2 is given. Okay, and also the angle of bend is given. Okay, so what are the informations are missing that we have to find out? The informations are missing is the velocity v1, okay, and velocity v2, and the pressure at point 2. These informations are missing. So the P1 and P2 are equal. So what P1 and P2 are what type of pressure are equal P1 and P2? The static pressure. Okay, because there is a no static loss because of this friction, but there is a conversion of kinetic energy into potential energy. Okay, so because of that, there is a pressure loss that we will see. So the static pressure are equal, but the total pressure at point 2 are not equal. P1 and P2 are not equal since the height of the elbows are given. So this factor has to be considered. So let's start. So here you can see the V1 was which was unknown. So we are going to find V1 first. Okay, so V1 is equals to Q1 over A1. So Q1 was given in liter per second. So we converted this liter per second into meter cube per second. So which has become zero point 0.3 meter cube per second. The diameter of the point 1 was given. Okay, so pi d square by 4. When we resolved it, we got the value 4.24 meter per second. Okay, so after calculating this by using the formula continuity equation, okay, Q1 is equals to Q2, because there is one inlet and one outlet, so the flow will remain same. Okay, so the Q1 is equals to Q2. That means A1 V1 is equals to A2 V2. So we simplify that. The finally V2 is equals to V1 d1 by d2 d1 over d2 whole square. Okay, so when we put the values of all the known values, so finally we end up with the velocity v2 is equals to 9.5 meter per second. Okay, so these two values were unknown, so we found it. Now the another variable which is missing, that is P2. Okay, this P2 is going to be changed because of this vertical head. If this vertical head is negligible, in that case P1 is equals to P2 100%. Okay, but since the elevation is given, because when the fluid is moving from here to here, so it's converting its kinetic energy into potential energy. So because of that, the total pressure is going to be changed. Okay, so this we are going to see now. P1, so we are applying the the Bernoulli equation, okay, to find out the value of pressure at point 2. Okay, so here P2 is equals to P1 over gamma 1 is equals to Z1 V1 square over 2G. Okay, this equation is in the form of pressure head. Okay, in the form of meter. because this is Z. And P2 over gamma plus Z2 is equals to Vt square over 2G. So now we have to find out P2. So we simplify the equation. So P1 plus, this is the factor. So P1 was given 70 kilopascal and we substituted all the values. Okay. And finally we got the value 18.7 kilopascal. Okay. So now the pressure at point 2 is known. Okay, now it is very easy to develop the equation for the conservation of linear momentum. So the all the unknown values are known, all the parameters at section 1 and at section number 2 are known now. So now we can develop the equation for the conservation of linear momentum. So here, so first we are going to develop the equation in the x direction. Okay, so in the x direction, before that I want to show you one more thing, because here you see this is our control volume. Okay, so in that case we are considering the basically the anchoring force. Okay, what is the anchoring force? That is F pipe. This is the anchoring force which is acting on the pipe. So what are the component of anchoring force? This is the force in the x direction. So the net force acting in the x direction. So this is the equation we can develop. So this is at P1. Okay. So P1 is equals to the force acting in x at point 1. So the pressure force P1 A1 is equals to cos, okay, Px1, P2 A2 cos theta in x direction. Force acting at the pipe, the reactive force or the anchoring force in x direction is this. And basically this, the equation of conservation of momentum we have written straight away. So QP is equals to, yeah, rho Q is equals to V2 cos uh, cos theta in at the exit and the component of velocity at the inlet, okay, in x direction. So now we are going to substitute the values of all the variables. Okay, so in that case, so students, so this is the journal. So students, so this is the journal equation of the conservation of linear momentum in the x direction. Okay, so let's see, because you see in the x direction it seems that the velocity is coming horizontal. Okay, here theta is equals to 0 in the x direction. If this is the x direction, so in this direction the will be the angle between the flow and the uh, the velocity, okay, or angle between the flow angle between the flow and the x-axis is 0. Okay, all right, the flow axis, I can say that. So here, but this equation is general equation. Maybe if it is not 0, if it is making the inlet velocity is making some angle, so it is going to be some velocity. Okay, so the some component. So here the cross section, this is the pressure force. So if it is acting with some angle, so it is become P1A1 cos theta. Okay, same if it is making some angle, the exit making some angle, so it is P2A2 cos theta. Okay, and similarly the force, the x component is like this. So definitely, so this is going to be the fx component. Okay, so we're going to write down. So this is a journal equation. Okay, so now and then QP is the mass flow rate multiplied by V2 minus V1. So V2 is equals to, if it is discharging with a particular angle, so V2 cos theta. If entering with a particular angle theta, so V1 cos theta. Okay, so this is how basically we develop a journal equation of all the forces in the x direction. Okay, So now let's put the value of all the variables. So here you see the P1, it was given 70 kilopascal. We inserted here. Okay, the area we calculated, we put it here, and theta. Since it seems the entering the direction of flow and the x-axis are in a same parallel to each other, so theta is equals to 0. Okay, so since this equation is general equation, you can use it for any L type of elbows. Okay, so here again P2 we calculated 18.7 kilopascal, and then area A2 which is reduced, and cos minus 60 degree. So here you can see you can develop an equation. Okay, here take the axis. All right, so if this angle is 120 degree, if this angle is 120 degree, so what about this angle? This angle is going to be 60 degree. So do one thing, make the component of x and y. So this is x component and this is y component. Okay, so this is v2x, this is v2y, and this is v2x. So v2x is negative, or this angle will become what? This is become cos. If this is theta, this is 60 degree, so this will become cos. Okay, so this will become cos 60 degree minus. Okay, so we'll take it minus here, and cos 60 degree, they took it basically with the equation cos minus 60 degrees is equals to minus cos 60 degree, so this will become minus. Okay, is equals to QP. Q was given. Okay, rho density was given, and V2 is equals to 9.55 we calculated. Okay, and cos 120 degree. Okay, it discharges with 120 degree. Sorry, cos. Okay, or you can take the component. Okay, don't take cos, take what is the component in the x direction. Okay, what is the component? V2 cos 60 degree. This is the cos 60 degree in the negative direction, so put the negative sign here. Okay, so you must take the negative sign here in the bracket. Okay, otherwise it will be wrong, because it is going to be minus, so you have to put it minus. Okay, so this is going to be minus, you can write down here the minus. This is wrong, cos 120 degree is fine, but if you are taking 9.5 multiplied by cos 60 degree, so you must use minus sign because of its direction. So since they are using cos 120 degrees, so automatically the minus will come here. Okay, because they are making component in this way. Okay, from here, that's why. Okay, then again minus from the formula. Okay, this is from the formula. V1 we calculated. Okay, and this cos theta V1, what is cos 0 degree. Okay, so when we simplified that, we got the value of force, the anchoring force in x direction is minus 7946 Newton. Okay, so this is the force in the x direction. Now the force in y direction, we use the same general equation. For the y direction, we substituted the values, and finally we got the value in the, we call it y direction. Okay, we are not considering z direction. Okay, it can be z. Okay, it can be z, but we are considering its y direction. Okay, but here in the problem they took it as a z, so I am taking, you can take it y, no problem. Okay, so no problem with the assumption, whether it is y, z, it's up to you. Okay, so it has to be clear. So y component, the force we calculated is 382 3829, 3824 Newton. Okay. Now the resultant force can be found by summing up square sum of the two forces with under root. So we substituted the value, and finally we got the net resultant anchoring force need to hold that elbow, that is 8818 Newton. Okay, at what angle it has to be supported, the angle can be calculated this alpha pi force arc tangent inverse 382 yani sigma Fy over Fx, okay, is equals to 154.3 degree. Okay, so we have to anchor the, okay, so this is going to be anchoring force. Okay, if this is the elbow, okay, if this is the elbow, so the anchoring force supposed to be like this from the x-axis. So this is going to be 154. Okay, this is going to be 154. Okay, it is clear. As I said, if this is the elbow, okay, and this is your force F, okay, this is your force F of pipe. So what is the angle of 154? Take the horizontal x-axis. Okay, so this will become your 154 degree, 154.3 degree. Okay, so this is the value. Okay, so this is how we analyze the anchoring force, how we calculate the anchoring force by using the conservation of linear momentum equation. So that's all for today. Thank you very much.